All right. Hello, everyone, and welcome to our education session. Thank you so much for joining us this morning. Kerwin and I are here. We're going to talk to you about challenges and opportunities of gas flow measurement and ventilator testing. We really appreciate your time today. And before we get started, just going to introduce ourselves real quick. So my name is Benz. I'm leading the US entity of IMT Analytics. We are based in Tampa area in Florida. So I'm originally from Switzerland, but I've been living there for the last 2.5 years now. And when me originally be from Switzerland, there's some good and some bad news for you guys. So the bad news is you're gonna have to deal with my really bad German accent for the next hour. But the good news is I've recently been back in Switzerland and I brought some Swiss chocolate for you guys today. So you can pass this around and have some. All right. Yeah, while you're passing that around, a little bit more about me. So I've been in the medical device industry for more than 12 years. Started off as a tech support engineer for a company manufacturing ventilators mainly. Then also been part of technical training. So I trained a lot of people on how to service ventilators. Then moved to IMT Analytics, more focusing on test equipment to actually test ventilators, held different roles there, like in marketing as well, and now in management. So overall, about 12 years of experience in that field, and happy to share our thoughts today with you guys. So with that, I'm going to hand it over to my colleague, Kerwin.
Hi, I'm Kerwin Sanger, and believe it or not, I'm not Swiss. I am based in San Diego, or near San Diego, and but I have been with a really great Swiss company, IMT Analytics, for about 9 years now. Great engineers, really good high quality products. Sorry, we're not supposed to do sales here. But a little bit about me, I've been in the industry for more than 30 years. I've been in engineering roles, tech support, technical training. I did a lot of ventilator service training for several different vent manufacturers. I've done production and repair center management, and now I'm the business development director for IMT. So I've been around for a while. Okay. Any questions so far? We want this to be a really nice interactive session for you. So at any time you have a question, feel free to interrupt and ask. The more the feedback we get from you, the better we'll be able to pace this whole program. We can speed it up or slow it down. I know you've got lunch at the end of this, so we'll try and get you out of here on time. First of all, before we start, can I have just a show of hands, who is actually currently working on ventilators or anesthesia equipment? Good mix. And how about who has never worked on a ventilator or anesthesia equipment? Okay, a few. That's all right. So we have a good mix, so we have a good place to start. We're going to try and kind of gear it towards everybody. Okay. As Daniel and I said in our introductions, we've both been in the industry for a long time, and we've actually faced a lot of these challenges that we're going to talk about today. Probably a lot more than we're going to talk about today. We'll limit to about 3. But there are actual challenges that we've seen through tech support and through our own experience doing service training and things like that. And now that we're both working in the test equipment industry, we see that there's a lot of good opportunities that can be had by learning more about your test equipment and by the test equipment manufacturers to help solve some of these challenges that we're going to talk about today. Okay, let's just jump right into this. The challenges that we're going to talk about, we're going to kind of keep it to 3, and we probably won't get into any real specifics with regard to brands of devices. So we're going to try and keep it a little bit general. But if you have a specific situation that you're facing, feel free to ask. The first one is complex and unclear measurement setups. Okay. The second will be ensuring that your gas flow analyzer is set up properly or correctly. And third is understanding the test sequence that you have to do, okay? And what the manufacturers are requiring you to test. A lot of that is just understanding what you're actually testing really helps. Okay, what do we mean? Let's jump right in. First challenge, complex and unclear measurement setups. I've got some examples here. This is an actual couple of photographs from a ventilator manufacturer's service manual. And they've done a fairly good job of showing you how to set up your test equipment with their ventilator. But of course, they've chosen one piece of test equipment. You may have others. You may have to adapt this photo to your equipment. They've done a pretty good job with showing all the components. You've got the analyzer there, and you've got all the connections to the ventilator, including the pressure connections. Some of them are a little bit hard to see. There's a pressure tap that's teed in right here. But for the most part, it's all there. On the other side, you might not really be able to see where they've teed in their oxygen sensor. Okay, but this, as I said, this manufacturer did a pretty good job. They at least gave you some photos, and they gave you some labels to the photos. The challenge comes when you have to say, okay, I don't have this analyzer. How do I make my analyzer fit into this situation? And we'll kind of help you out with that. Another example, another manufacturer, they did a nice kind of drawing, but they don't really give you any details here as to which ports you should use or what connections you need to make. So again, you might have to really know your test equipment and know how to apply it to this ventilator before you can actually do the test they want you to do. In our third example, they just basically say, hey, tee in your analyzer, you know, and measure, in this case, it's VTI, which is, you know, inspiratory tidal volume. And they don't really give you a lot of guidance. So we see this all the time. You may only have one piece of flow analyzer test equipment, and you might have to use it on a whole myriad of ventilators or anesthesia machines. And the setups for each one can be different. So it's important that you know your device. So the opportunity here for that challenge, of course, is learning more about your device. The more you know about it, the easier it will be to adapt to all these different situations. Questions so far? Okay. Depending on the analyzer you use, your setup can look completely different. In that first example, we show this analyzer, and we have a fairly complex setup with everything teed in. There's a tap for the pressure. There's oxygen can be teed in. You might have to hook up a trigger cable to tell the analyzer when you're in inspiration or when you're in exhalation. And by using a different analyzer, you might have a much more simple setup. Okay, so understanding your analyzer and how it goes into each one of these setups is very important. So what can we do? We can select an analyzer that allows for simple setups. If you have a complex analyzer, then you'll have to learn exactly how it works and how to set it up in all these different situations. But using a simpler analyzer is much more helpful. A lot of times now we're seeing the all-in-one devices. This means it's pretty simple. You can connect the patient circuit to one side and a test lung to the other, and all the parameters that you need to measure are done through its main flow channel. So you don't have to tee in oxygen, you don't have to tee in pressures, you don't have to add a trigger cable, things like that. So knowing your system, getting one that's simple, all these things go to help minimize the risk of measurement errors that are caused by these setups that are inappropriate or complex. Any questions about setups? Anybody face any of those type challenges? Doing okay? Good point. I'm glad you brought that up too, because we are talking today about ventilators and anesthesia equipment for the most part, but there's a lot of other applications that you can use your analyzer to measure. Okay, no matter which analyzer you have, chances are it will have pressure ports that you can measure pressure on. It might have high or low flow ports. It can do high flows like wall air systems. It might have low flow ports where you measure infant systems, things like that. So again, it's real important that you know your equipment and you know how to set it up, because you can use it for a lot more than just one or two things. A lot of times people get to go through maybe a OEM's training class and they see a particular analyzer being used in that class and they think, oh, I have to have that analyzer to test that ventilator, and it can only be used for that. So then you might have colleagues that are hoping to use your analyzer to do other tests, and you won't be sharing it with them. So know your analyzers well, share them with your colleagues, and just be open-minded to use them on multiple different devices. Okay. Now, something that might help you in that is to know how to set up your analyzer correctly. Okay. There are critical gas settings on all the analyzers that you should know and be familiar with. Okay, there's something called gas type. We have gas standards. We have, and those are both used for flow and volume measurements. And then we have things like trigger settings that are used for breath-based parameters, things like rate, tidal volumes, PEEP settings, things like that. We'll go through each one of these and show you and talk about each one. And then there are the measurement parameters themselves, and we'll see that a lot of ventilators or equipment manufacturers call things by different names. So if you know, for example, that rate on your analyzer is the same as breath rate on a ventilator, or in some cases frequency on a ventilator, then you'll be able to apply it more easily. Okay, I think Daniel will go into more detail on those in a moment. Question? Okay. All right, let's talk a little bit about gas type and gas standards. Why it's important. So if we're trying to measure a tidal volume, which is one breath worth of volume, okay, and we're talking about gas that we're delivering from a ventilator. If we take that gas, let's say we capture a certain amount of it in a container, and we start to change the environmental or physical conditions of that gas, what happens to that volume? So for example, if we increase the temperature, the volume does what? It increases, right? If we increase the humidity of the gas, what happens to the volume? It goes up again, right? If we pressurize the gas, however, what happens to the volume? It comes back down. So here we're changing the condition of the gas, right? So we need to know what that is so that we can measure it with our analyzer. Okay. We also can change the characteristic of the gas by changing the gas mixture. We may have just air, we may have just oxygen, or we have some mix in between. In some cases, you might also measure other gases, but in most cases, we're talking about either air or oxygen or some mix of those two. But either way, if you change the concentration of oxygen, you're going to actually increase the volume a little bit, okay? So we have the same number of molecules in our container, but depending upon the condition and the characteristics of that gas, the volume might change, okay? Why is it important for us to measure accurate volumes? What's that? Exactly, patient safety, right? We want to make sure that we give the patient enough gas, but not too much gas because we can injure them, okay? Very important. All right, let's talk a little bit more about gas characteristics. We have things like the gas density, viscosity, and the viscosity coefficient. Those are pretty much dependent upon what gas you're measuring, right? And that is something you might have to actually enter into your analyzer. You can say, I'm measuring air, I'm measuring oxygen, I'm measuring a mix of the two, okay? We'll talk in a minute about some analyzers can tell you what the mix is. Then we have the condition, again, of the gases. For example, we have the differential pressure over a flow channel resistance. Some analyzers use a small resistance in the flow to create a difference in pressure so that they can convert that to a flow measurement. There are other devices out there that use things like hot film anemometers. I don't know if you're familiar with those, where they have a small film or wire that's heated and it's in the airstream, and they determine flow based on the cooling of that heated element. But that would be temperature in the gas. They need to make sure they know what temperature the gas is to see how much it's cooling the actual wire. There's the gas pressure itself during inspiration and exhalation. There's humidity, and then of course oxygen concentration. Those are all things that are typically measured by your analyzer. And I know oxygen concentration is really a characteristic of the gas, but like I said, some analyzers, you can set them for something like air O2 auto and measure the oxygen concentration during the flow measurement, okay? So all of these things are used by your analyzer to calculate actual flow rates, and we call that pressure, measurement, gas flow measurement, all right? We call it measurement. We'll see in a moment there's difference in measuring and displaying. So when we use gas flow measurement, we're actually measuring the live actual conditions and characteristics of gas. And we can call that a gas standard called ATP, or actual temperature and pressure. Okay. There are many different gas standards used in our industry, and we can apply those gas standards to this measurement and display them in something else. So we can actually take our mass flow measurement and we can add an offset to it and display it in a different gas standard. Who's heard of STP? Standard temperature and pressure. How about BTPS? AP21. There's I think, what do we have? 17 different gas standards, 18 different gas standards out there that are being used. Most common we'll see ATP, STP, and BTPS. Okay. When we apply that a different gas standard to the actual measurement, we call that flow displaying. So you'll see that there's a difference between actual measurement and what might actually be displayed. Well, why would we want to do that in the first place? Let's take a situation where the therapist is actually ventilating a patient. Okay, and when they do that, especially in critical care patients, they'll probably put a humidifier in the circuit. Okay, that heats and humidifies the gas that we're putting into the patient's lungs because we've bypassed the nose, which normally does that for us. Okay, but what happens to our gas, right? If we're starting here at the ventilator, and let's, for example, say 500 milliliters is coming out of the ventilator, it goes through, and what happens to its condition? It does what? It gets warmer and it gets humidified, right? So what does that do to the volume? So at the patient, the volume is actually increased significantly in this case, okay? When you add heat, humidity, you go from room air or room temperature up to body temperature and 100% relative humidity, you increase by quite a bit. a little bit more than 10%, actually. And so ventilator manufacturers have made it easier on the therapist, and they said, well, let's display what we think the gas will be when it gets to the patient, not what the actual output is. So on the ventilator settings, the therapist would say, okay, I'd like to deliver this 560 mils to the patient, so that would be on their settings. And then the ventilator would tell them, yes, I sent 560 mils to the patient. When in reality, that ventilator sends only 500 and expects the conditions to be changed by the humidifier, and then the volume changes, okay? So we call body temperature and 100% humidity, relative humidity, BTPS, body temperature pressure saturated. And that is another gas standard that we just talked about, okay? Well, what happens to us as technicians or engineers when we want to test that ventilator? Has anybody ever tested a ventilator with a humidifier in the circuit? It doesn't happen, right? It's really hard on your test equipment when you do that. So we're going to be testing with just a plain circuit. Again, we'll use that 500 mils for a, or the 560 mils for a setting. But we know that the ventilator is going to do what? Only put out 500, right? So since the gas conditions don't change, when they get to our analyzer, what happens to the volume? It stays the same, right? It's still 500 mils. So now it looks like when I look at my analyzer, I've got a problem. I'm not measuring what my ventilator is saying I should be measuring. Because remember, a lot of times ventilators have both a setting and a measurement, right? They actually tell you, oh yeah, I sent this tidal volume. If it's being displayed in BTPS, when we measure it without the humidifier, we're going to have a big difference. Okay. So we start out with a setting of 560, we deliver 500, no change in the gas condition, we measure 500 at the analyzer, right? So what can we do? Because now we're not comparing the same standard. We're basically comparing BTPS to ATP. Okay. Well, your analyzers have a setting on there called a gas standard, and you can select BTPS. Okay. As a matter of fact, whatever ventilator you're using, and not all of them do BTPS, some do ATP, STP, AP21. You want to make sure that whatever you're testing, you set your analyzer for. Okay. And I know this sounds like, oh, this makes total sense right now, but I can't tell you how many times people have said, hey, there's something wrong with my analyzer. It's off. It's not reading what my ventilator's telling me. And so what I'll do is I'll say, well, how about you make different settings on your ventilator, right? Go up to 1,000 milliliters or 800 milliliters, or go down to 200 milliliters, and tell me what the analyzer's reading. Is it reading about 10% high on all of those, or low on all of those? And if so, you probably have a mismatch between your gas standards. It happens all the time. Okay, so now if we have our ventilator showing BTPS, we know that it's delivering less than what's set. The analyzer is measuring that same 500 mils, but now it's going to display 560. So what we have is a match where we're actually comparing apples to apples, right? BTPS on both sides. Okay. If your ventilator's not delivering in BTPS, and it's not always obvious, you might have to look in that manual. You might have to actually contact the manufacturer, but make sure you do so that you can make sure you're measuring in the same gas standard that the ventilator is delivering in or displaying in. Okay? Questions about this? Has anybody faced this problem before? No one? All right. Then let's move on to the other next important things. I'm going to hand this off to Daniel, let him talk for a while.
Right.
And let him tell you about trigger settings.
Thank you, Kerwin. Yeah, so really important topic again, gas standards. Just make sure that your analyzer always matches the gas standard of your device under test. Whatever it is, whether it is a ventilator, an anesthesia machine, or something else, that whenever it's about measuring gas flow or volumes, that's really very important. So that was kind of the first sets of settings that we wanted to discuss with you, and these are the most important ones. Make sure that the right gas type is selected on your gas flow analyzer and the right gas standard. And these two things are the fundamentals to measure accurately flow and volume, right? So, but as you may know, gas flow analyzers, you don't only measure flow and volume, you also measure so-called breath-based parameters, right? So things like tidal volumes, peak pressure, peak inspiratory pressure, and stuff like that. So to measure these, the gas flow analyzers, they analyze actually the measured waveforms of flow and pressure and then calculate these values based on timing parameters, okay? So these are typical waveforms you would see on your display when you have like a ventilator connected to your gas flow analyzer. You see like pressure rising during inspiration, for example, and going down to a base level during exhalation, and then this is the next cycle that starts over here. And then depending on the mode of your ventilator, your flow might do something like this. It's going to rise, deliver an inspiratory tidal volume, and then in exhalation you will see some air coming back from the patient or the test lung in our test setup, maybe back to the ventilator. And now one task of our gas flow analyzer is actually to measure different parameters based on this timing of these waveforms. We call them breath-based parameters. And to do so, the analyzer needs to know what is an inspiration phase and what is an exhalation phase, okay? Somehow the test equipment must know, okay, now an inspiration starts and now it changes to exhalation, and then at some point the next inspiration phase starts. So we do that with so-called triggers. So at some point the device is going to know, okay, now I start with an inspiration, then it starts calculating all the inspiration parameters, and then at some point it's going to be triggered. Now it changes to exhalation, then it calculates values from there, and then with the next inspiration it starts over again, because this can depend on settings on the ventilator. So how do we do that? And again, this is important for many different, there are kind of, I don't know, 20 plus different parameters that you can see on typical gas flow analyzers, all based on these trigger settings. So if your gas flow analyzer doesn't trigger, then you can't measure these parameters at all, okay? So how do we do that? We have settings in our gas flow analyzers where we have to tell the device when it should trigger. And if we don't have these settings correct, then either we have no measurements of these parameters, or they can be significantly off. So if my timing of my triggers are not correct, not close enough to the reality, then that can lead to calculation errors. For example, here we see a typical flow waveform during an inspiration, and my gas flow analyzer needs kind of a start and an end to see, okay, for what time do I have to calculate my flow and mathematically integrate it and say, okay, this is my volume. So in this example that is shown here on the screen, my trigger settings, if they are off in timing, means in my reality, the breath starts here, but now I'm actually being triggered too late. And on the other side, my inspiratory phase ends here, but actually my trigger only triggers too late. Then I miss a certain volume here, actually, my calculation, right? And also on the other side, here it goes negative to exhalation. I calculate a little bit of this negative flow also still in my inspiration. So as you can imagine, my tidal volume that is being calculated by my gas flow analyzer is then going to be quite a bit off, right? So the trigger settings also have an impact on the accuracy of my measurements. So how can we define trigger settings? So that typically in gas flow analyzer, you will see 3 different settings. One is called the trigger source, then a trigger signal, and then a trigger level. So as a trigger source, we can typically select between like a flow channel of the device or a pressure port. Sometimes you will also see external trigger input. So there are a handful of ventilators out there in the market. They have a trigger output. So they can tell you with a digital signal when they start an inspiration phase and when they change to exhalation. So you can also use that digital signal. But very typically you have like a measurement on the gas flow analyzer that you want to use for triggering. And then you can select the signal. Either it's typically the flow waveform, or you could also use the pressure waveform to as a trigger signal for your analyzer. And then you need to tell it based on what waveform you selected, okay, at what threshold it should interpret it as a trigger. So I could, for example, say, okay, if my flow rises on a rising edge and it crosses the 3 liters line, then I want to say, okay, this is a sign of a start of an inspiration. And if it crosses a certain value on a negative, on a falling edge of the signal, then I say, okay, this is now my trigger for the end of the inspiration phase. And then the next trigger starts the next inspiration phase. Does that make sense so far? All right. So the challenge then sometimes is to find out, okay, which signal. So if you take a look at your waveforms on your gas flow analyzer or the software that comes with it, then challenge is very often to find which signal do we want to use for triggering. And let's have a look at some examples here. The thing is, we want to choose the signal that allows us to set trigger settings that are as close as possible to the reality. Okay, so let's have a look at an example here. So let's say this is our flow waveform that we see on the ventilator or on our gas flow analyzer, and we can see it starts here. This dotted line here is actually the actual real start of the inspiratory phase, and then it rises and it falls, and here with this dotted line, we know that's actually when it changes to exhalation. So let's say we want to set trigger settings on this flow waveform. Do you think that's, and sorry, one more thing to mention. When we set our levels, we don't want to go too close to that 0 line, because sometimes we have signal noise on our measurements, and we don't want to cause this noise actually to trigger our analyzer. So do you think this is a good signal to trigger on? Who thinks it's a good signal? Raise your hand. Who thinks it's a bad signal? Okay. You think it's a bad signal? Well, yeah. Yes. Correct. Correct. So this is actually not a real good trigger signal, because for example, here at the beginning of the inspiratory phase, it looks pretty good because it has a rise, a steep rise. So we could say, okay, let's say if it crosses like 2 or 3 liters per minute here, then we can say, oh yeah, this is the start of our inspiration phase. And that gives us a very accurate trigger, very close to the reality. But at the end of the inspiration phase, here, when it switches to exhalation, there is not really a nice change in the signal. So we can't really set a proper trigger setting there. So if we would just use the same threshold as for our start trigger here on a falling edge, then you would see we have a huge mismatch of our real inspiratory phase, for example, and the one that the ventilated test equipment actually measures. So this is just an example to show you, if you have these trigger settings inappropriately set, then this can make a big difference in like measurements like rate or an inspiratory time or a peak pressure and things like that. If we take a look at the second example here, we have some positive flow through the analyzer during inspiratory phase, and then some negative flow through the analyzer in exhalation phase. So this is very typical in test setups when you have like a ventilator and a test lung, and flow goes through your test equipment and comes back to the ventilator. So do you think this one is easier to trigger? Yeah, right. Because here we can now, remember the first waveform we had very little change in signal over here. So with this one, it's quite easy. We can set the start trigger here on a positive flow, let's say 2 or 3 liters per minute, and then an end trigger on the negative flow. And then it's very easy to quite accurately trigger our breath cycles. However, as you can see here in these dotted lines indicated, we are still a little bit delayed, right? Because the signal is not very steep, all right? And this again can have some impact in accuracy of some measurements. So if we look at the third example and last example, this is then a very good trigger signal, because as steeper these signal slopes are, the better and more accurate I can trigger my analyzer. So long story short, if you want to select the trigger signal for your analyzer, make sure that you choose the waveform that has the steepest slopes at the actual breath transitions. That makes it very easy and to accurately trigger the breath cycles. So this sounds very challenging, right? So let me ask you, the ones of you that are using gas flow analyzers, how many of you have ever touched the trigger settings of your analyzers? No one? Okay, that doesn't surprise me, because in typical ventilation test setups where we have positive and negative flow through our analyzer, we have waveforms that look either like this if we are in a pressure controlled ventilation, or like this in a volume controlled ventilation. And as you can see, the flow waveform always has this very nice rising and falling edges at the transitions of each breath phase. And additionally, we have a zero baseline that doesn't really change with the settings of the ventilator. That's why our gas flow analyzers, very often, you will see if you go into the trigger settings of your gas flow analyzer, you will see they have always per default, the trigger settings are going to be on the flow curve, and they will have trigger levels around 3 to 5 liters per minute as a start trigger and a stop trigger. And these triggers work well in, I would say, 95% of your applications. So that's probably why you guys never had to touch them. Okay, so this is really important to know. It's actually, in many cases, you don't have to touch them. But now I want to talk to you about a case where you do have to touch them, because then it's important to understand what it means. So has anyone ever tested BiPAP ventilators? You guys? BiPAP, okay. What's special in these measurement setups? Yeah. And also in the setup, is there something typical in the measurement setup? Very often in BiPAP ventilation, you have a defined leakage that you have somewhere in your circuit system, right? Yeah. In BiPAP ventilators, very often, if you have like your ventilator and your analyzer and your test lung, then you have a defined leakage somewhere to simulate a patient interface, like a mask, for example, that has a leak port. And then the challenge in such a situation is when this BiPAP ventilator applies pressure, then it inflates the test lung. And then when it releases pressure, then the air flows out of the test lung, but it actually leaves a leakage here. So it never goes back through the analyzer, right? And the problem here is then you have a situation, as we discussed earlier, that your flow is never really going to go negative back through your device. And since we have learned, as we have learned earlier, your default trigger settings on gas flow analyzers are typically based on exactly that to happen, that the flow goes negative. Otherwise, they don't work anymore. So in such a BiPAP ventilator test situation, the flow waveform cannot really be used sufficiently to trigger anymore. So if you have an analyzer on the default trigger settings and you measure such a situation, then it's not going to measure a rate, for example, or tidal volumes and stuff like that. So here we have to think about what else can we do, right? So take a look at the pressure waveform. Does this pressure waveform looks like a good signal to trigger based on what we discussed earlier? Yes, yeah, but it is pretty good, right? We have like here at the start of the inspiration phase, it rises rapidly, and then at the end of the inspiration phase, it drops, right? So it's pretty good, yeah. So let's have a look at that. So typically in a BiPAP ventilation, we have two pressure levels called IPAP and EPAP. And in such a situation, we would then set like the trigger for a start of an inspiration phase, the level of here, like this is EPAP, the lower pressure level, plus 1 centimeters of water pressure. And then a stop trigger when it drops from like that IPAP level by 1 centimeters of water pressure. And let's say the first settings, you have a BiPAP ventilator and you have to test that. And the first settings that they ask you to use is an IPAP of 6 and an EPAP of 2. So then we can say, tell our gas flow analyzer, okay, use the pressure waveform, and a start of an inspiration phase is when it crosses the 3 centimeters of water pressure line on a rising edge, and a stop trigger if it drops below 5. So that will allow us to trigger here, right? But then let's say the next settings that you need to test is an IPAP of 8 and an EPAP of 4. And as soon as you change these settings on your ventilator, your gas flow analyzer is going to go, whoop, no measurements. Why is that? Because now we moved up the whole pressure levels to a higher level, right? And now, indicated by these dotted lines, our old trigger settings are no longer going to work, because now my lower pressure level where I have my trigger settings, that's 3, is never going to be reached again. So that's why now the analyzer cannot trigger anymore. So in such a situation, you would then have to amend your trigger settings on the gas flow analyzer and adapt them to the new situation and say, okay, I'm going to have to move them up to 5 and to 7, and then only, your gas flow analyzer can measure the parameters again. So as you can see, if you have to change the trigger settings, then it can be quite challenging actually to figure out the correct settings. So make sure that you familiarize yourself with the trigger settings. Again, in 95% of the situations, you probably don't have to care, but if you have a situation like this, typically BiPAP ventilators, then you will have to adjust your trigger settings accordingly. Otherwise, you'll not be able to measure these parameters. Any questions about trigger settings? Okay. The last thing on the settings side, as Kerwin already mentioned, there are a lot of different parameters that gas flow analyzers can measure. So typically about 25 or more, depending on the brand or the make you're using. And one other important point is that we make sure that we take a look at the right parameters. So sometimes, for example, ventilator manufacturers call something like peak, that's the peak pressure during the inspiration phase. And another ventilator manufacturer calls that PIP, for example. Or as Kerwin mentioned, rate, frequency, stuff like that, right? So they can have the same thing named differently. And also your gas flow analyzer uses some kind of terminology. So it's important that you understand how does it translate to your actual device that you are testing. And also we have different units of measurement, right? So for example, pressure you can measure in millibar, or you can measure in centimeters of water pressure, or you can measure in some different units. So we need to make sure that it matches with what we measure on the gas flow analyzer, that it matches what is displayed on the ventilator. Because the ventilator manufacturer, what do they tell you? They tell you, okay, you need to compare this value on the ventilator screen with that value on your analyzer. So you better make sure that you have it in the same unit, right? Otherwise, it can be off. Typically on gas flow analyzers, you can customize your screens and you can make sure that you set up the right units for this application and make sure that you understand what measurements you need to look at. Okay, so now we talked about a lot of different settings. We talked about trigger settings, gas, we talked about gas type and gas standard, and we talked about the units of measurement and the actual parameters. So what are the opportunities here opposed by modern gas flow analyzers? So one important thing, if your gas flow analyzer offers that features, we highly recommend you create profiles. So many gas flow analyzers out there allow you to save all your settings for a specific device you figured out, maybe by testing or by looking at the manual, to save all that as profiles. So typically profiles include like gas type, gas standard, trigger settings, and all your measurement screens. For example, here you can see an example of a measurement screen. So sometimes you can arrange them differently, you can colorize them differently, and all these settings can go into a profile. So you can have a profile, for example, for ventilator A and a different profile that you use for ventilator B. So each time when you have the same application again, you can then, instead of going through all the settings again, you just load that profile and it sets it up correctly for you. This really helps reducing the risk of inappropriate settings and reading errors at the end of the day. And another thing is make sure that you, sometimes your gas flow analyzers may have some advanced features that help you determining the best possible trigger settings. For example, if you have analyzers where you can see the waveforms on the screen, then that helps you to figure out which waveform is good to trigger on, right? Which is the one with the steep rising and falling edges on the signal. And you can sometimes also even measure on the analyzer to figure out the correct or the suitable threshold. And sometimes you can also find graphical support. For example, in this case, in this screenshot, you see there's a graphical indication of your trigger setting, what it actually affects and what it means. That can be very helpful as well. And in the latest generation of gas flow analyzers, there's also something called auto triggering. So they can analyze the waveforms in real time and then decide themselves which one is the best one to trigger on. Just imagine how helpful that is if you have to change the trigger settings based on the settings on your ventilator you have to test. Okay, so very important, make sure that you check what your gas flow analyzers have to offer as helps to figure out all these settings. Have you guys faced any of these challenges so far that we discussed? Some of them? Okay. All right. Yeah, so the last one we want to discuss with you is understanding the sequence and valid ranges defined by the manufacturer. So what do we mean with that? Sometimes you will see examples like this where it's quite a bit of a sequence. They tell you to test. So first, there's something you have to do at like 0 pressure, and then typically you have to measure different pressure levels, for example, and compare it to what you measure on the gas flow analyzer, right? In an ideal case, it would say, okay, set the pressure to 10, and then your gas flow analyzer should be between 9 and 11. Right, that would be an easy case. But sometimes you see things like this where it's very complicated. So here they ask you to apply pressure and then calculate your upper and lower acceptance limit yourself based on the measurement on your gas flow analyzer and on the ventilator. So there's a whole procedure, and they figured out that this is quite complicated, so they even added in the appendix, they added calculation examples, so what you have to do. So we simplified it for you a little bit. In total, in this case, we have to go, they ask you to go through 9 steps of taking a look at measurements, then calculate some valid ranges, and then interpret if your measurement is actually inside that calculated valid range. So, of course, it's important to be trained on the ventilators you're testing, but procedures like these can be very cumbersome and very prone to errors, right? You really need it. It takes you a couple of minutes to read that and understand what you actually have to test. Here's another example. This is from a different ventilator manufacturer. Here it's about the different flow scale points. So very often you have to do like 10 liters per minute, 20 liters, 50 liters, 100 liters and stuff like that. And here it's the same thing. You have to first take a look at, do a setting on the ventilator and then measure it and then calculate the acceptable ranges with a percentage value and then kind of interpret whether this is within the range or not. So it's pretty much the same story here. It's quite cumbersome and there's a lot of potential for misinterpretation here. So the last opportunity linked to that is, on some gas flow analyzers out there in the market, you have guided applications or test sequence that they offer on the gas flow analyzers. So these applications, sometimes they are on like on a computer software, sometimes they run actually on the device. And what they do is they guide you through the whole procedure, and they can also take the measurements automatically then and also interpret these measurements. So they can do the calculations for you automatically and then judge whether the measurement or the result is actually in the range or not. And then they can give you pass-fail results right on the screen. And also they can save all these measurements and then at the end create a PDF report and that you can then print and attach to your work order. So there are gas flow analyzers out there that have these sequences running on the device or on a separate software that can really help you overcoming all the challenges we discussed so far, because they make the calculations for you and make sure that you follow the sequence correctly. And they also make sure that all the settings are correct because they are designed for a specific ventilator. So it already makes all the settings for gas type, gas standard, trigger settings, and everything in the background for you. So this can be very helpful then. And of course, this also helps to improve your productivity because you don't have to do all the calculations yourself because it's done automatically. All right, key takeaways from our sessions. Number one, ensure that you understand the features of your gas flow analyzers. As Kerwin mentioned, right, you need to know what is measured in the flow channels you have and the pressure ports so that you can adapt it to the setup actually that you probably see in a service manual of a ventilator manufacturer with a different device or even no device, so that you understand how you have to use it. And then pay special attention to the settings that we discussed. If there's just one thing I want you to remember is the gas standard. Make sure that the gas standard matches the gas standard used by the device under test, because this can really lead to a lot of reading errors. And that's also the thing that we see most out there in the field, because as I mentioned, the trigger settings typically work with the default settings, but the gas standard is really something that you need to make sure that it's correct. And then take advantage of these advanced features. Sometimes you may have a gas flow analyzer and you just start using it, you just measure values and you don't really take the time to figure out, okay, what features are there that could allow me to make my life easier. So it's really worth spending some time with the user manual, make sure that you understand what the gas flow analyzer has to offer, and very often you will find helpful tools to overcome these challenges in the field. All right, that was it, what we wanted to show you today. We have a booth number 103. If you are interested in our gas flow analyzers, we would be happy to show you how our gas flow analyzers help you overcoming these challenges. And now we want to open the Q&A session. So if you have any questions, please feel free to ask. Are you on? No.
Can you hear me now? So just from, all the tech support that we do, some things that we hear a lot, I always tell people, make sure you warm up your device, your analyzer, give it at least 5 minutes. If you're traveling around and it's been out in the cold, let it warm up to room temp before you even turn it on. Then zero it out, okay? Go ahead and in almost all analyzers, there's an auto or zero calibration that you can do. Make sure you zero it out so you're starting from baseline. Then do your gas standards and gas types. And lastly, trigger. And that takes care of, as Daniel said, probably 98% of the problems that we see out there. And I can't tell you how many times I've said, did you do the zero calibration? And people go, well, we send it in for calibration once a year. It's like, no, that's the user calibration. It's not the, yes, a lot of analyzers say send it in for actual calibration, but there are calibrations that you need to do before you use it each time you use it. Same way with it, it might have an oxygen cell. It's important that you calibrate that oxygen cell as well. As we said before, if you're using a gas type example on our analyzers, and you use air O2 auto, it uses the oxygen cell to tell you not only the gas concentration, but if that oxygen cell is not able to measure, then it won't be able to tell you other parameters as well. You might have to switch to air only or oxygen only and test that way without the actual oxygen sensor. But those are all things to kind of keep in mind. Warm up the device, gas type, gas standards, trigger settings, and make sure you zero it out before you use it. Anything else we can share with you? Help? Any questions? Go to lunch. Get out of here.
All right. Thank you so much.
Please.
Thank you.
Look at that. We spared you a minute. Have another chocolate. Anybody else wants one? Pass it around again.
Chocolate.
Yeah, save me one. No wrapper on that one.